Okay, we are at the last section, rolling motion of a rigid object. Let's look at uh, the PowerPoint. So you can see this is a time lapse photograph. There's a cylinder with a green light at the center of the cylinder, and there's a red light at the edge, the rim of the cylinder. And so as you roll the cylinder, you can see that the center green light moves in a straight line, and the red uh, point on the rim moves in a path called a cycloid. So you can see that there's a the center of mass is moving straight, and the edge is making these look, these humps, um, like it almost looks like a bouncing ball. Okay, so the velocity of the center of mass is ds dt. Well, that's equal to r d theta dt. Um, S is equal to r d theta. So ds dt is equal to r d theta dt. Since r isn't changing, d theta does change, but r doesn't change. And what is d theta dt? That's equal to r omega, the time rate of change of uh, of angle is the angular velocity. Uh, Similarly, the um, uh, the acceleration of the center of mass is equal to dv/dt of the center of mass, and so that's equal to r d omega dt, and d omega dt is equal to alpha, so that's equal to r alpha. So the velocity of the center of mass is equal to r omega, and the acceleration of the center of mass is r alpha. Okay, you can have different types of motion. You can have pure rotation, um, where you can just imagine a disc spinning. So the center of mass has no velocity, but the uh, the disk is spinning, so you have the velocity is r omega at the top, but it's also r omega in the opposite direction at the bottom. And then you can have pure translation, where you can imagine it sliding on a frictionless surface, not rolling, uh, where you have all of them are traveling at the velocity of the center of mass. And then you can have a combination of the translation and rotation. So you have the velocity uh, of the center of mass and the r omega. So the velocity is the two of those, uh, and that's equal to 2v cm. Uh, okay, and the kinetic energy is 1/2 I uh, omega squared, and the kinetic energy is a combination of both the rotational 1/2 I center of mass omega squared plus 1/2 m r squared omega squared, um, because r omega is the velocity, so 1/2 m v squared is uh, 1/2 m r squared omega squared, uh, and that is there is your k equals 1/2 I uh, omega squared plus 1/2 mv squared. Um, all right, let's analyze this rolling object going down a hill. You have the uh, kinetic energy is equal to the sum of the rotational kinetic energy and the translational kinetic energy. And we're going to pull out the v squared. Um, so it's 1/2 uh, ICM over R plus M. Um, and so the kinetic energy plus the potential energy, uh, the kinetic energy is one half uh, the uh, moment of inertia divided by r squared plus m times the velocity of the center mass squared plus mgh. Now let's take mgh to the other side, so that it becomes positive mgh. So we'll have 1/2 I over r squared plus m times v squared. And let's divide both sides by m, the capital M you see there. So you'll just end up with 1/2 I, ICM divided by mr squared plus 1, m divided by m is 1. And on the other side, you get just gh. And that's where we get to this, if we take to the, now we divide by the 1/2 I over r squared plus m, we'll see that, or we changed it to 1/2 I over m r squared plus 1. If we take that, we divide both sides by that, we'll get v squared equals 2gh over 1 plus I divided by mr squared. Take the square root of it, and that's where you get the 1/2. So the velocity of the center of mass is equal to the square root of 2gh divided by 1 plus the moment of inertia divided by mr squared. Okay, let's look at a ball rolls without slipping down the incline, starting from rest. At the same time, a box starts from rest and slides down the incline, which is identical to incline A, except that it is frictionless. Which arrives at the bottom first? The ball, the box, both arrive at the same time, or it's impossible to determine? Well, it's actually the box will arrive, because all the gravitational potential energy of the box Earth system is transformed to kinetic energy of translation. For the ball, some of the gravitational potential energy of the ball Earth system is transformed to rotational kinetic energy, leaving less for the translational kinetic energy. So the ball moves downhill more slowly than the box does. Okay, and I believe that, so the box arrives first. And that ends our chapter 10. And